review earlier in the semester about composite functions. And at that time, I tried to build a case for the fact that we use composite functions a lot in everyday life. The idea of a composite function is that we have a chain of events, more or less. If I think of having two events, the first one has to happen before the second one does. The first one has an input resulting in an output. The second one starts with the output of the second one, or the first one, and has its own then conclusion. And if we look around the room, I can see you all used it appropriately in a personal way, because I don't see any socks over your shoes. Okay, so the first action is getting, well, I hope I don't see any socks over shoes. The first one is getting a pair of socks out, and the output is socks are on my feet. And then the second function or action is that I'm going to have shoes, and so the second action starts with the socks on my feet, and then ends with shoes on my feet. And so we can't do the second without having the first. Same thing happens with our mathematical composite functions. If we look at functions f of x and g of x, and I say I want you to build a composite function of those, and we're going to call the result h of x, what would be our way of expressing a composite using f of x and g of x? And there's two ways you can do that. Well, what if we start with g of x? That's going to be our first function. And once we're done with that, so g of x is the output of g of x, of the function g. But I'm going to use that now as a starting point in function f. So now g of x is not the output of function g, it's now, how would you describe that? As we see it here, g of x is the input. Well, it would be the input of function f as we see it here. Let's go back and look at that, because without this, we're really going to be lost. In this case, this is the input of function f. Why? Because it sits inside the function notation we have there. It is the input of function f. It also happens to be the output of function g. And so we would start with function g of x, find an answer, use that answer. It's kind of like what we did with the derivatives in a way. Find the answer and put that answer inside then the other function. The other way we could do that, anyone have a clue as to what we could do besides having f of g of x? Sure, we could have g of f of x. That means that I'm going to start with what function? Well, I'm going to start on the inside. Now listen to my terminology, because I use this a lot. I'm going to start on the inside function. I'm going to start with f of x, get an answer from that, and put that answer into function g. So g is the outside function. Kind of sits out there, doesn't it? And f of x is inside. It kind of sits inside. So my terminology is accurate when I use those words there. We have to understand this in order to do the chain rule. And so the whole section of 2.5 is the chain rule. Let's go on and let's see if we can't figure some more information out here. The chain rule says that y equals f of u. Now let's just look at that just for a moment. Y equals f of u. What is the input in this statement right there? Yeah, okay. U is the input. What's the output? Y. We could also say the output is f of u. Yeah, either one of those ways of saying it. So the input is u, the output is y, or f of u. It's a differentiable function. What does it mean that it's differentiable? Yeah, it has a derivative. You can find the derivative. The derivative exists. Any of those phrases would work. Okay, so this function, you can find a derivative for it, and it does exist. Okay, now we go over here. U equals g of x. Take a look at that. What's the input in this? X. What's the output? G of x or u. Now, in this problem, in this right here, this is what, an output, you say? But what was it over here? An input. It's an input. So I could say that since u represents g of x, here's my f of g of x. I can replace that with g of x. Okay, so here's an example where, this is an output. This is an output. And then yet I use that very same output as an input in another function. Well, let's go on and break this apart. That happens to also be a differentiable function. Okay, then y equals f of g of x. Well, how does that come about? Again, g of x is the input in function f. G of x is also represented by the letter u. And isn't that what I have over here? So we're kind of talking in circles, aren't we? In a way, it sounds like it to me, because everything's related, to relate to everything else. Okay, now, here's what we come up with. Remember that dy dx is another way of expressing a derivative. When I use the notation dy dx, what does that x represent? Input or output? You have to know this in order to be able to do these problems. So x represents input or output? Input. What does y represent? Output. So I'm going to find the derivative of y with respect to x. Now, which of these three highlighted expressions, can I represent with dy dx? And what I want you to focus on is what's the input and what's the output. Okay, is that the derivative notation for this? No, because the input up here is u, not x. Could it be this one? The input is x, but the output isn't y. What about down here? The input is x and the output is y. Okay, so dy dx is what we're going to find here. Well, what about dy du? Yeah, look at the input, look at the output. This derivative, let me get a different pen here. This derivative goes with that, because the input is u and the output is y. The input is u and the output is y. What about this one? Yeah. And again, all we're doing is focusing on what's the input and what's the output. Where do I find the input here? Where it's down here, the x. The output is u. The input is x. The output is u. And so this one is the one we're using to represent here. Okay, this is why we call it the chain rule. Notice that I've got two derivatives multiplied together. Now, again, as I said before, when I introduced this notation, the purist would have us say, don't think of these as a fraction. It's just notation, dy dx. And I'm thinking, no, it's not. There's a little more to it than that. There are differentials. Differential y divided by differential u divided by differential x. Now, differential u here represents the input of something, but up here represents the output. So they're not quite the same thing, but even those purists would say, well, if you look at that, those things can cancel. And what are you left with? Dy dx. What were we trying to find? dy dx. Okay, so the chain rule says if you want to find the derivative of a composite function, if you can break it apart into the two separate functions and take their individual derivatives, then just multiply them together. You get the derivative you want. A little more to it than that, but that's basically what we're doing here. Okay. Now, the other thing, though, is that there is another set of notation we could use, because we're used to seeing the f of x notation, and we're used to seeing f of g of x, and that's what I've got here. The derivative with respect to the input x of the composite f of g of x. Now, again, what does g of x represent in this f of g of x? G of x is the input expression. It is also, in and of itself, a function. And that function sits inside the notation for a function f. So it is the input, and let me switch colors here again. It is the input, and yet I'm going to call it not the input, but I'm going to think of it as the inside function. It is the input, its output becomes the input of function f, but we also then use the words inside, outside, because that function literally sits inside function f. Now over here, do we see, look at this piece right here. What does this say? Now what's that prime mark mean? Derivative of, so this is the derivative of the inside function. F prime of, so if g of x is the inside function, then f of whatever is the outside function. So what is this piece? Derivative of the outside function. Yeah. So if we think now not only of what is the input and what is the output, but what functions are we dealing with, and is one function inside the other? I've got other ways to make it a little clearer to you, so if you're a little fuzzy on this, just hang in there. I've got more ways to express this. But this is getting the notation to us. Okay. Let's see. What we're going to do, let's go to, I'm watching the clock here, let's go to this problem though. The first thing I want to do is, let's write it as the composition of two other functions. Because the key here is, can we see a composite function? If you can't see a composite function, it's a little harder to do this work. Okay, so if I'm going to look at this, let's call h of x, and we can let y equal h of x, and let's say that it's f of g of x. So we're going to identify f of x as the outside function, and we'll identify g of x then as the inside function. So go back to this. Now, here's the first key. If I told you x equals 3, what's the first thing you would take care of to come up with a value for y? What would you do, Hema? Yeah, I would first of all find 3 plus 2. Okay? That's the first thing I would do. So that makes g of x x plus 2. Okay? And when you think about that, what's the first order of operations here? What's the first thing I would do? Well, the first thing I would do is take care of what's inside the parentheses, x plus 2. So x plus 2 is my inside function. Once I knew what that value was, it's 3, what would I do with that? I would take the result of this and raise it to the negative 1/2 power. So my outside function is x to the negative 1/2 power. Let's see if that works. If this is true, then I can come down here and I can say, okay, it's f of g of x. That means f of x plus 2 That means that I'm going to use x plus 2 as my input expression into function f. I'm going to take x plus 2, and everywhere I see an x, I'm going to, so that would mean that I'd have to place it here, and that, does that put me back to where I was? Yeah. So that, the one thing then is, if you're a little confused, just ask yourself, okay, if I knew a value for the input, x is 3, what's the first thing I would do? First thing I would do is add plus 2. Why? Because it's inside. It's the parentheses here. Okay, so that's the first thing. Now, we haven't taken the derivative yet, and actually this problem isn't even asking us to, but hey, let's go ahead. Let's try it anyway here. So we're going to take the derivative, and I want the derivative of this. I'm going to write it one more time here. Okay. So we're going to find the derivative of that. So that means I'm looking at dy dx, the derivative of my output with respect to my input. And remember now, the derivative of this, we can do it a couple of ways. One is, if I know what g of x is, can I find the derivative of g prime of x? If I know g of x is x plus 2, the derivative of that is just simply 1. Well, what about the derivative of f of x? It sits there by itself. Let's see, I'll go back up so we can see it. That would be negative 1/2 x to the negative 3/2. Good. Yeah, always subtract 1, remember, so I already have a negative 1/2. Okay. If I'm going to, I don't want to go back and throw the u's at you because I don't want to confuse anyone more than maybe you feel you're confused already, but let's look at it this way. This is going to be the derivative of the outside function times the derivative of the inside function. Now I can see already that I'm going to have to go back and kind of do a little bit of cleanup for you here. Let's see. If I'm going to do it this way, I'm going to have to go back and use the u's. So give me a moment here. I'm going to go back here. We'll just go up here and do it. It might be easier, and you can always go back and look at the videos and see how we did this. If we go up here and we say let's let u equal, and I'm going to say let u equal g of x, x plus 2. That's not too hard, is it? We're just going to let u equal that. Down here then, I can say this is the derivative of u with respect to x, and that's still going to equal 1. That's not changing anything. Okay. If I'm going to let u be x plus 2, then I'm going to have to let y equal u to the 1/2, negative 1/2. Think about it. If u is x plus 2, is that the same thing as u to the negative 1/2? Okay. Well, what does that mean down here? Well, that means then that I've got dy du. Remember, this is y equals u to the negative 1/2. So this would be negative 1/2 u to the negative 3/2. Okay, now the chain rule says this, and we're using the chain rule here, so I'm going to put it up here so we can remember. Chain rule. We've got the outside function, that's negative 1/2 u to the negative 3/2. times the inside function, which is just simply 1 at this point. So let's see, that should just be simply negative 1/2 u to the negative 3/2 if I multiply by 1. But I got a problem. This is supposed to be dy dx. Do you see the problem I've got? What's the input variable? What's over here? Can't do that, okay? Can't do that. I'm going to have to go back now and in place of u put in what it represented, yeah, in order to be true to my notation. My notation says the input variable is x. It has to be there. I can't let it sit there as a u because that's not being true to my notation. So my derivative then is this. Now that's the first way of looking at it. That's going back and using, you know, dy dx is equal to dy du times du dx. Remember, when we do this chain rule, those differential du's cancel out, and we're back to, this is what we did. We have the dy du, that's this, and the du dx is here, and we, you know, basically, we didn't actually go through and cancel those, but they cancel by nature of what they are. But let's look at it now with the alternate, and the alternate is this. Let's go back and look at this. Are we doing anything different? This represents the inside function. What does this represent? Inside function also, right? What does this represent? Derivative of the outside. What does this represent? Derivative of the outside. It's the same thing. Okay, but the notation looks a little different, but it's always going to be the same thing. But here's what it's going to look like in our work. So I'll put another line down here. Let's see, this is y equals x plus 2 to the negative 1/2 power. We're going to have to decide which one is easier to work with. Sometimes it's going to be easier to use that dy, du, dx, you know, the chain rule. Other times it's going to be easier to use this method. I want the derivative of y with respect to x. I'm going to rewrite this. It looks almost like it's times 1/2, and that's not the case. So just make sure it looks like an exponent. I always ask myself the question, what's the outside function and what's the inside function? We've already discussed that. We know that the inside is x plus 2. The outside is to the 1/2. Now, bear with me on this. You can put anything you want. But if I had just something as silly as smiley faces in there, and I said I have something to the negative 1/2 power, you tell me the derivative is negative 1/2 times those silly square, you know, negative 1/2 times those things to the negative 3/2, right? Doesn't make any difference what you have in here. The outside function is taking a quantity or an expression to the negative 1/2 power. And I'd end up with this. Now, we're not going to keep the smiley faces. They're kind of cute, I think, but we're not going to keep them. Instead, we're going to go back and remind ourselves what it is we actually have behind those smiley faces, and that is x plus 2. Then we take the derivative with respect to x of which part? This is of the outside function. This is now of the inside function. Okay? So we're doing the same thing. We're taking the derivative of the outside function, and if you need to, cover it up literally or figuratively. Cover it up and say, what am I doing? I'm taking something to the negative 1/2 power. That's the last thing I'm going to do in this function. First thing I'm going to do is add 2, and then the last thing I'm going to do is take that answer to the negative 1/2. So my outside is raising to the negative 1/2. I take care of that outside function derivative first, then I take the derivative of the inside. Do I get the same thing? Yeah, I get the same thing. Okay, now this is what we call the chain rule, and we just need to kind of work our way through it, and I'm not necessarily going directly as the book has it, so if you read the book, that's just going to reinforce and bring more understanding to you if you're needing that. But let's take a look at this. I'm given y equals 2 the square root of u, and I'm given u equals 5x plus 9. Can you build a composite function from those? Would you know which one is the inside and the outside just from looking at this? Which one is it here? Which one's inside? Pardon? If I'm given this information, you know, these two quantities, I'll put them in, I'll highlight them here. This is one, okay, and then this is the other. If I'm given that information, can you see a composite function? Nick, what do you see there? Yeah, because
the u is the input.
yeah, here I only have the value u, and so if I have an expression, so we could say this is 2 times the square root of 5x plus 9. That would be my composite function, because I can replace this u with the expression 5x plus 9. Now, this problem's not asking us to do this. This is where I'm taking off my own little tangent, puns intended here, my own little road side trip here, but we can do this. dy du, which of these am I going to use? Well, better use the one that has an input of u and an output of y. So I'm going to, if I'm going to use dy du, okay, so dy du is going to come from this one. I'd be better off, I think, if I started with, let's move this stuff down here. I'd be better off if I started with maybe rewriting that function first. Maybe doing something like y equals 2 times u to the 1/2 power. Because now if I want dy du, I would have 2 times what's the derivative here? 1/2 u to the negative 1/2. Okay? So this one is coming from there. If I'm going to do du dx, which function am I going to use? I'll look for the one that has the input of x and the output of u. So that's going to come from this one. And so du dx is simply 5. Okay. Oh, thank you. Chain rule. Okay, and I want to, if I want to chain these together, I want to chain them in such a way that I end up with dy dx. And so if I want to find dy dx, I would have to chain them. Now actually it's multiplication, right? Does it make any difference in what order I multiply? It's kind of nice when you do it so that you can see them side by side, but you know, I could do du dx times dy du. It doesn't make any difference. It's nice when I do it the other way around, but it doesn't have to be that way. Because even here my du's cancel. So let's see. Du dx is 5. dy du is, that's actually going to be 1, isn't it? 2 times 1/2. So it'd be u to the negative 1/2. But again, can't stop there. Why not? Yeah. Yeah, x is my input, and I don't have it here. Okay, so I'd have 5 times, what was u? 5x plus 9 to the negative 1/2. Now, the rule for me with you is you never leave an exponent to be negative. So I would want you to go one step more and write it as 5 divided by, you can either say 5x plus 9 to the 1/2 power, or that's the same thing as saying 5 divided by, the square root, 5x plus 9. Either one of those I would be happy with. Okay. Now, again, to help you see that both of these, and actually the next slide takes care of what we were talking about now, but we're going to still continue to work on it. Let's do this. Let's do it the other way. Keep thinking about these not as two separate ways, but actually one way with two different notations. So if we're looking at the function y equals 2 times the square root of 5x plus 9, first thing I'm going to do is rewrite it, 5x plus 9 to the 1/2 power. And then if I look for the derivative of y with respect to x, come on, you can write it. There we go. If I'm looking for the derivative of this, again, my first thought is order of operations. What's the first thing I do in this function, and what's the last thing I do? The first thing I do is my inside function. The last thing I do determines my outside function. So what's my outside function? Who's saying what? I heard some good mumbling. I just need to, yeah, Aaron? So my outside function is taking the square root of something. Is that what you said? Yeah. Yeah, again, if I put some smiley faces here, and I ask you to find out what is, what's the derivative of 2 times something to the 1/2 power, you'd probably say it's 2 times 1/2 to the negative 1/2 power. Okay, again, if you need to, do something as silly as, not maybe literally, but figuratively, as little smiley faces in there. Just cover that stuff up, because it's just something to the 1/2 power. And what do you do with the derivative of something to the 1/2 power? Well, you do this, and subtract 1/2. Then it's going to be the derivative with respect to x of, and again, this is taking the derivative of the outside function, and now we have to take the derivative of the inside function. And so it's the derivative of 5x plus 9. Okay? Now, we should get back to the very same answer we got before. Should. Hopefully we will. What's 2 times 1/2? Just 1. Okay, so there's my 5x plus 9 to the negative 1/2. What's the derivative of 5x? Plus 9, rather. So we have just 5 there, because it'd be 5 plus 0. Okay. Is that the same thing we got before? Yeah. Now, which of these methods do you need to use? You really just need to know both. Certain problems are easier with certain processes. And some problems are easier if they're, to look at and to use this method with. Some of them, especially our application problems, are a lot easier if we can separate it out and look at the derivative of, each of the individual functions there. Okay. Like I said, we've already talked about this. I don't think we need to talk about it anymore. This is called the general power rule. If I ask you to use the chain rule, I consider this to be the chain rule. Why? Because this is the derivative of the outside function, and this is the derivative of the... Are we doing anything different than we were before? It's just using different notation. So if I ask you to do the chain rule, this to me is you also using the chain rule. Understood? The book may separate it out differently, so be careful with the web assign, but your answer should still come out to be the same on that. Okay. Well, let's just practice. Have some fun practicing here. Yeah, this one said use a general power rule. Well, yeah, okay, whatever. Okay. First thing we have to do, well, maybe the second thing we have to do. First thing I'm going to do is I'm just going to rewrite this. Okay. Trust me, not all these problems are square root problems. Seems like it, giving you 3 of them now in a row. Okay. What's your inside function and what's your outside function? That's the next thing to determine. And you can answer that by asking yourself the question, if I knew what t was, what's the first thing I would take care of? And what's the last thing? And so the first thing would be inside the parentheses. That's the inside function. The last thing would be taking the square root. That's the outside function. Okay, so if we're going to use the derivative or find the derivative of this, you like stars better? Okay, we'll put stars over it this time. You know, what is the derivative of something to the 1/2 power?
The 1/2 times
The stars.
the negative 1.
Yeah, absolutely. And so, we'll just take 1/2 times whatever that is to the negative 1/2. Now, again, we're not going to use those in real life, so we'll go back here and just fill in that this is that amount. So this is your derivative of the outside function. What's missing? Yeah, derivative of the inside. This is the work I need to see on your papers. I need to see you put this step down. The derivative of the inside function. Remember, I'm not going to put this to the 1/2. The 1/2 power is the outside function. We're just working with the inside function. So we have, we can do some algebra along the way. We can say this is 2 times the square root of 2t squared plus 5t plus 2 times, yep, that's it, 4t plus 5. Now I've asked you to show me the derivative, take the derivative, and then show me at least 2 more algebra steps. Some of these problems, there's not going to be 2 more algebra steps to take. 4t plus 5 divided by 2 times the square root of that is just about as far as I think we need to go with this. Some problems there'll be more to do. Others, I always want a positive exponent. Yeah, always give me positive exponents. Okay, some of you I can tell are bored. You think this is so easy. You're wanting a challenge, aren't you? Right, Katie? You ready for that challenge?
Yeah.
You got this. Here we go. Okay, now, the challenge comes when we put more than one rule together in the same problem. What's one of the rules we're going to have to use? The quotient. Is that in our inside function or in our outside function? Inside. So the inside function is going to be using the quotient rule. What's the outside function eating? Yeah, well, it's going to be, the power rule. So we're going to use the chain rule on this one. Very good. Okay, so here we go. The derivative of y with respect to x equals and again, imagine me putting smiley faces or stars or something over here. What would you do with something squared? Either 2 smiley faces to the first power Okay, so it'd be 2 times something to the first. Well, what is that something in here? Yeah, you got to write the whole thing out, so I'm going to give myself a little more room here. So it's 2 times 6 minus 5x divided by x squared minus 1. You can put a 1 up there if that helps remind you. But that's the outside function you just did. Right here. Now, times the derivative with respect to x of what? Yeah, write it out just as you see me do it. If you need to, give yourself a little bit of a hint. This is the outside function. This is the derivative of the inside function. Okay. This piece is pretty much done. I don't have to do any work on the outside piece at all. But the inside piece now, I have to use the quotient rule. So it's a good time to practice the quotient rule. Remember, you're going to write out those derivatives inside this. So it's the denominator times the derivative of the numerator, plus or minus. How do you know that? And again, do you have a method? Or are you just, hoping that you don't forget? As long as you've got a method. Mine is always that when I subtract, almost everything I do in the mathematics, if I subtract, if I'm dividing, I'm subtracting, like the terms like I explained on the video. Okay, so denominator, derivative of the numerator minus the numerator times the derivative with respect to x of the denominator, and I'm done, right? No, because I have to take it, everything divided by the square of the denominator. Okay, so in our work, we have 2 lines of showing the derivatives. One is showing the chain rule, so this is showing the derivatives for the chain rule, and then this one is showing the derivatives for the quotient rule. Keep my eye on that clock down there. Okay, so we've got 2 times the quantity 6 minus 5x, x divided by x squared minus 1, times x squared minus 1. Derivative of 6 minus 5x? Negative 5. Okay. Minus the 6 minus 5x. Derivative of x squared minus 1? 2x. All of it divided by x squared minus 1 quantity squared.